Hello everyone, here we are, talk about regression, the essence of regression. So let's get started. So what I want to talk about today is an assumption of regression, and it is, as it says up here above me, normally distributed residuals is an assumption of regression. Let's talk about what that means. All right. So in talking about this assumption of normally distributed residuals, let's just take a look at what a residual is, and we'll take it from there. All right, so let's have a frequency distribution, and here we have our y-axis, our vertical axis, and on our y-axis, let's say we have some outcome variable. We'll go ahead and we'll call it organizational commitment. That's been a favorite outcome variable of ours. And so here we have org commitment. And over time, I've forgotten how to spell commitment again. In the past, I forgot how to spell it. And then I learned how to spell it, and I've forgotten how to spell it again. Is it two M's? Is it two T's? I don't remember anymore. So my producer is going to have to tell me how to spell it, but it'll be a later tape. So right now I'm going to go ahead with this. So this is organizational commitment, and let's say we have a measure of that where someone can get a score from 1 to 50. And then on our x-axis, here we got our x-axis here. This is our horizontal axis. Let's look at this in as simple of a way as we can. So let's look at this in terms of like simple regression, where we have one predictor variable on the x-axis. And let's say that predictor variable is job satisfaction. Okay, so in our model, we have one predictor variable called job satisfaction, and we have a measure of job satisfaction. Let's say on that measure, you can get a score anywhere from 1 to 60. Here, let me get this x out of here because it's getting in the way of the value here. And again, we have the x-axis. Okay, so what we're doing with our model, okay, with this one predictor variable in it, is that we're seeking to have the model predict values on the outcome variable measure. And the outcome variable here is organizational commitment. And the predictor variable in the model is job satisfaction. And so based on participant scores on job satisfaction, on the predictor variable measure, the model is going to make a prediction as to what person's scores would be on the outcome variable, in this case, organizational commitment. Okay, so in that way, we're trying to predict from our model, based on person's scores on the predictor variable, what person's scores would be on the outcome variable, organizational commitment, which is, well, again, our outcome variable. Okay, so what we start is we draw what is called a regression line, and the prediction that comes out of the model of person's scores on the outcome variable measure, organizational commitment, is based on person's scores on the predictor variable measure. And so let's say that a person gets a score on job satisfaction, that predictor variable, and let's say the score is 10. Okay, so we follow it up, and what we have right here on the regression line is the predicted variable out of the model as to the person's score on the outcome variable measure, organizational commitment. And that value is whatever that value might be. I'll just give it an arbitrary value here. Let's say it's 8. Okay? So based on the person's score on the predictor variable, job satisfaction, on that measure of job satisfaction, predictor variable measure of 10, then the predicted value coming out of the model as to the person's score on the outcome variable measure, organizational commitment, in this case, is a predicted value of 8. Note the predicted value coming out of the model is right here on the regression line. Okay, so let's keep going here. Do a couple of more, okay? So let's see, we have another participant, and their score on job satisfaction, let's say, is 15. Okay, well, we follow that up from the person's score on the predictor variable measure of job satisfaction. Follow it on up, and we have the predicted score, again, right there in the regression line, coming out of the model, as to that particular participant's score on the organizational commitment outcome variable measure. So this is the predicted score coming out of the model. And so let's say the predicted score for that person on the outcome variable, organizational commitment, let's say is 10. Okay, let's do a better 10. There we go. There we go. And then let's say we have another participant whose score on the predictive variable measure for job satisfaction is, let's say it's 18. There we go, 18. Yeah, we'll work on my numbering here. Yeah, I'm gonna get this. I just know we are. There we go, 18. And so we follow that up, and we get a predicted value out of the model. Again, right there, that predicted value can be found in the regression line. For this particular participant, the predicted value coming out of the model as to this participant's score on the outcome variable measure for organizational commitment, let's say is 12. Okay? And on we go like this for all of our participants in our sample. They all get a particular score on the predictor variable measure for job satisfaction, somewhere along this range from 1 to 60. And for each of those scores on the job satisfaction measure, we go on up to the regression line, and that's the predicted value coming out of the model for each of those participant scores on the outcome variable of the organizational commitment measure. Okay? All right, now you've heard this before. Well, I think you've heard it before. I guess it's where you'd be in terms of looking at the videos. But there is a video on the homoskedasticity assumption, so homoskedasticity, and I talk about similar ideas there on that video. But I mention it here because the first thing I want to show you what a residual is, because we're going to talk about normally distributed residuals. You should know what a residual is. But I also want to talk with you a little bit more broadly than that in terms of what I see as the 3 essential values in regression. Okay? There are 3 essential values. And if you can keep in mind these 3 essential values, it'll go a long way for keeping things straight in your mind about what you see with regression. And they are depicted right here. Well, almost. I got to add a couple of more things. Note that what we have here are predicted values out of the model based on participant scores on the predictive variable measure, okay, of job satisfaction. But that's the predicted values coming out of the model. Then for each participant, we have an actual observed score on the outcome variable measure. So for this particular participant, let's say they have an actual observed score right here. So for this participant, the predicted value coming out of the model is 8, but that same participant's actual observed score in the outcome variable measure is right here. And so it's clearly quite different from the predicted value coming out of the model. So this is the observed score, okay? So predicted score out of the model and that participant's actual observed score on the outcome variable measure. All right, so our first essential value in regression is the predicted value coming out of the model. Our second essential value in regression is the person's actual observed score on the outcome variable measure. And then we have the difference between the two. So here, there we go. Or the error in prediction between the predicted value coming out of the model and the person's actual observed score on the outcome variable measure. So that's the difference. And that is known as the error in prediction or the residual value for that particular participant. So there you have your 3 essential values in regression: the predicted value coming out of the model, the participant's actual observed score on the outcome variable measure, and the error in prediction, or the difference between the predicted score and the observed score, the residual. All right, so those are the 3 essential values in regression: predicted score, observed score, residual. All right, so that's what the residual is. And as I'm going to depict for you in a moment, that is one of our assumptions of regression, which is that those residuals are normally distributed. And so here we have another participant, and here is the predicted score for that participant right here. And their actual observed score, let's say, is up there, considerable distance from the predicted score out of the model. Find the person's actual observed score in the outcome variable measure. And so here we have, the difference between the two, or the error in prediction, the residual for this particular participant. And then finally, we have this particular participant and their predicted score out of the model based on that person's score on the predictive variable measure. And here is this person's. Let's have this model be a little bit better than it's been so far. So here is the person's actual observed score on the outcome variable measure. So predicted score for the participant and their actual observed score in the outcome variable measure. And here, just a small error in prediction, just a small residual. Model did a good job here for this participant. The predicted value came quite close to the person's predicted value right here, came quite close to the person's actual observed score on the outcome variable measure. So here the residual value is right here, and it's small. It's a small residual, small error in prediction, again called the residual. Okay, and so you'll notice, and I've talked about this elsewhere, and that is that every observed value has a friend, right? So for any participant, they have an actual observed value on the outcome variable measure, and they have a corresponding predicted value out of the model. So every observed value has a friend. Okay, so always think of them as existing in pairs. And then you have the difference between the two, which is the error in prediction or the residual. All right, so those are the 3 essential values in regression. the predicted value out of the model, the person's actual observed value on the outcome variable measure, and the difference between the two, the residual. All right, so those are our residuals, and the assumption in regression that we're talking about now is that it is assumed that the residuals, or the errors, referred to as the residuals, or sometimes we'll see it referred to as the errors, are normally distributed. All right, so let's take a look at that. So this is going to go. So now let's talk about residuals and an assumption in regression, which is that our residuals are normally distributed. So let's take a look at what that looks like. Here we got it, right? Normally distributed residuals. We know what we're going into here. Okay, so we got this. I'm not drawing that well today. I don't know why, folks. Look at this, I'm all bowed here and stuff. Well, that's supposed to be a straight line. And this is the y-axis, and here we have the x-axis. And this is a frequency distribution. Okay, so that's a frequency. We have frequencies here along our y-axis, our vertical axis. And along our x-axis, we have standardized residuals. Now, this assumption of normally distributed residuals, it applies whether we're talking about residuals or whether we're talking about standardized residuals. But let's go ahead and put this in terms of standardized residuals. But it can be expressed either way. And so our residuals need to be normally distributed. That is an assumption of regression. And so, first of all, let me just give you an example of what a normal distribution can look like. I'm kind of nervous here in showing you. Given how lousy I drew this y-axis, I don't know if I'm in any shape whatsoever to draw you a normal distribution, but I'm going to go ahead and give it my best shot. So normal distribution can look like this. This is one example of a normal distribution where it can look like that. Now, that's not too bad. Let's go ahead and stretch this out a little bit here. Okay. Okay, so right down the middle of our normal distribution, here at the midpoint of our standardized residuals, we have 0. And then these residuals are in standard deviation units. That's how they're standardized, as residuals in standard deviation units. And so here we have 1, 2, 3. And then over here we have -1, -2, -3. And I don't think I spaced them out as well here as I did here, but you get the basic idea. You'd have equal spacing on each side. And so there are the standardized residuals, and it's normally distributed. So right down the middle we have we have 0, and it's symmetrical. So we have as many residuals above the 0 point as we do below the 0 point. So it's a nice normal curve. It doesn't have, well, in this case it's a perfectly normal curve, so it doesn't have any skew, doesn't have any kurtosis. It's just a nice, perfect normal distribution. And the assumption allows for some flexibility around this, so we can talk about it being approximately normally distributed, but the assumption is that we have normally distributed residuals, and that looks something like this. This is one example of what a normal distribution of residuals might look like. Okay, now that's not the only example of what a normal distribution of residuals might look like. You might have, as a separate example, but I'll put them both here on the same frequency graph. You might have this particular normal distribution of residuals might look like this. Okay, might look like this. Now, these would be two examples. Here's one example, normally distributed residuals. Here's another example of normally distributed residuals. Great. Either way, we've met the assumption of normally distributed residuals. But I just have a question to ask you. So just think about this, okay? Get this through your mind here. If you're building a model and you want a good fitting model, which distribution would you normally see? Now remember, there's no difference between them here. They both meet the assumption of normally distributed residuals, but one distribution is certainly preferable over the other for other reasons, for another very important reason. And so would you rather have a distribution of residuals, normal distribution of residuals like this, or would you rather have a normal distribution of residuals like this? Da 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 da. Yeah, okay, great. So, and you don't need to provide your answer in the form of a question. That'll be okay. The one you would rather see of the two, they're both normally distributed here, so that's not the difference between them. They both meet that assumption of normally distributed residuals. But the one you would rather see is this one here with the dotted line. And the reason for that is because the residuals are more tightly organized toward the middle part of the distribution, which means that your spread of residuals is less in terms of becoming larger and larger here on this side, larger and larger on this side. Well, they are getting large like that with this other distribution. Okay, it's more widely spread from the middle of the distribution out here to the tails. But with this one, it's more tightly organized toward the center of the distribution, and the spread of the residuals is not as wide. And we love that. And the reason we love that is because overall, our residuals are smaller. And as you remember from what I was talking about with you earlier on this video here that we're doing, if overall the sizes of your residuals, your errors in prediction between the values that are predicted from the model based on person's scores on the predictor variable measures and person's actual scores on the outcome variable measure, overall, the lower the residuals or the errors in prediction, the better fit of a model that you have. So when you look at this with these two normal distributions of residuals, we really like seeing this normal distribution with the dotted lines because it's more tightly organized toward the center of the distribution, not as spread out. That means that overall our residuals are smaller and we have a better fitting model. So we love that. We love better fitting models, and of course we always love it when we meet our assumptions. Okay, and we've met them in both cases here, okay? Both cases we've met them here in terms of normally distributed residuals, but we have the bonus with this one of it indicating a better fitting model. All right, so that is the assumption of normally distributed residuals and how you can look at that distribution of residuals and it will tell you something about how good of a model fit that you have. So there we go. We got 2 important points in one. Hello again. You may have noticed, I don't know how closely that you're observing these videos in terms of finding, noticing these fine details, but you might have noticed a little bit of like an edit, like a real quick thing for an edit. And if you notice that, it's because my producers were like going crazy. They're going, hey, wait a minute, you didn't sign it. Oh, well, we got to take care of that. So here we go. I'm going to sign this piece of work. My goodness gracious. I can't believe I forgot to do that. Here it is. Okay, I don't really have the room here to do it. I'm going to do it up here. Okay, so here's the signature. Oh, look, this is a lousy. Wait a minute. Who can get me something that works around here? Here, let's go like this. Maybe it works better over here. Nope. Anybody got a marker around here so I can sign this? Producers are running all over the place now trying to find me a marker so I can sign this. I'm glad I got through the video we just did. This thing obviously was right in the way to being empty. Okay, fantastic. Thank you. They're always at the ready to come in and rescue me. I love that. Okay, so here we go. Oh, fantastic. Look at that. There we go. We like to do a smiley face if we got a nose on it. Here, like that. And then here, we're going to go like, boy, that's, well, we are coming toward Halloween when I'm doing this, so I guess that kind of works. And then we got to put some hair on this, because if I can't have hair on the top of my head, which I really can't anymore so much, if I comb it a certain way, it looks okay, but it's I got to work on that nowadays. But if I can't have it happen easily anymore on me, gosh knows I can, here, put an ear here. I can have it happen on these drawings. Wow, were those the days? Not anymore. All right, so there we go. So that's kind of a weird smile, but it's, Halloween's coming up, so I guess it works. All right, like I said just a moment ago, you have a good one.